This lecture video will cover factors that affect solubility. Please read the OER textbook, chapter section 11.4 for more details. And in this chapter section, we are going to talk about three types of solubility. One is going to be solid in liquid. The second one would be liquid in liquid. And the last one would be gas in liquid. First, let's take a look at solutions of solid in liquids. Okay, so the process of making solution of solid in liquid would be dissolving solid into water, right? So in this case, this process is what we refer as dissolution. When you first dissolve solid in water, of those is going to be able to dissolve completely, right? So the reaction would go forward and it's going to be able to dissolve up until a certain point, and then the solid will no longer be able to dissolve anymore. And that's when the solid will start to precipitate out. And this process is what we call recrystallization. So if you're looking at the arrow here, you will see that the dissolution and recrystallization are the reverse process of each other. Okay, so dissolution is mean that the solid will be able to dissolve more in the solution, and recrystallization is mean that it's going to the solid will precipitate out of the solution. Okay, so this arrow that you see here, as I mentioned before, this arrow represent equilibrium arrow. So which means that at equilibrium, if you know how much the solid can this is what we refer as solubility. Okay, so solubility of a solute is going to be the maximum amount of solute that can dissolve in the solvent, okay, at equilibrium. Okay, so when we are talking about unsaturated solution, this is going to occur when it's not reached the equilibrium yet. This is going to occur when you have less of the solid than at the equilibrium point. What is going to happen is that if you continue adding solid, it's going to be able to dissolve more and more, right? So the solid will eventually disappear upon dissolving. So as I mentioned again, so in this case, solute would be able to dissolve more. Okay. Now the point where it is saturated, so this point is going to be the point is at equilibrium. This point right here, when you dissolve, when you add more solid to the solution, the solid will no longer dissolve. So it's going to be left as solid on the bottom of the beaker. Okay, so if this happens when you observe this, so this point right here is what we call equilibrium point. Is the point where solid will no longer dissolve anymore and it's contain the maximum amount of the ions available in the solution. Okay, so this is the maximum ions or the maximum amount of solute in the solution that is allowed. Okay, so if you add more, it's just not going to be able to dissolve. Next is supersaturated solution. Okay, so supersaturated solution is a solution at which the solution contains the amount of solute way more than at equilibrium. Okay, so this is like exceed at equilibrium point. How is this supersaturated solution can be achieved is going to come from, if you have the solution is already at equilibrium, right? You will see that you will have some leftover solid on the bottom. Okay, so in order to make this saturated solution to be supersaturated solution, what you are going to do is that you are going to heat it up. Okay, so as you heat it up, temperature is one of the factors that is going to affect solubility of the solid. Okay, as the temperature increase, it's going to allow for the solution to be able to dissolve more of the solute. Okay, so in this case, as this heat up of this solute is going to eventually dissolve all, right? So at this point right here, because this is already at equilibrium, right? And because you apply heat to cause this solute to be able to dissolve more. So that means the amount that is now dissolved in this solution right here is going to be more than at equilibrium. So this point right here is what we refer as supersaturated solution. Okay, so supersaturated solution is going to happen when you actually add more than the amount at equilibrium. Okay, so you can achieve that by heat it up. And because supersaturated solution has the amount of solute exceed beyond equilibrium, it means that the supersaturated solution is going to be very unstable. And because the supersaturated solution is very unstable, therefore, if you add any additional extra amount to this solution, the excess solid is going to precipitate out. Okay, so what do I mean by that? For example, this, right? So if you have supersaturated solution here, and this one right here, you will see that everything is able to dissolve completely, right? But however, at this point, we have way more solute than at equilibrium, beyond at equilibrium point. So therefore, in this case, if you disturb it, okay, by adding tiny bit extra amount, or even like scratching the beaker, or even scratching the size of the beaker, is going to cause the excess amount of solid to precipitate out. Okay, so eventually you are going to see that those amount that you add extra is going to just precipitate out of the solution. Okay, so it's going to be left, those solution that left over, this is going to be the solution at equilibrium. It's going to achieve at equilibrium again. Okay, so whatever extra is going to precipitate out. Okay, so what is the application of supersaturated solution? The application of this can be used in rock candy making. For example, if you add sugar, right, into water, and if you add to the amount that you cannot add any more sugar because it cannot dissolve anymore, what you have to do next is you just need to heat it up, right? So until the leftover sugar is all dissolved. And what you can do next is let it cool down. The reason for that is because as the temperature cool down, right, the solubility of the solid is going to become less soluble, right? So as it cool down, it's going to become less soluble. So that means all the excess sugar is going to be able to precipitate out. And that's how we achieve the rock candy making right here. So since you already see that temperature has an effect on solubility, so here is the example of the common substance and their solubility with the temperature. Okay, so the graph here represents temperature on the x-axis, and then the solubility is going to be on the y-axis. So this is represented in grams of the solute. So these are the solute. Okay, so grams of this. These are the amount of grams of the solute that can be dissolved in 100 grams of water at equilibrium. Okay, so this is the maximum value that you can actually dissolve them to achieve equilibrium. What do I mean by that? Okay, so let's take a look at sodium chloride, for example. If you're looking at sodium chloride, right, 10 degrees Celsius right here, if you're looking at this, right, so the amount of sodium chloride that can dissolve in 100 grams of water would be about 32 grams, right? So 32 grams of sodium chloride can dissolve in 100 grams of water at 10 degrees Celsius to achieve that equilibrium point. Okay, or another one would be, let's say, like lead nitrate here, right? So if you're looking at 40 degree, right, so you can see that it's going to be able to dissolve about 75 grams of lead nitrate, right, at 40 degrees Celsius in 100 grams of water. So that's what this graph means. Okay, so what can I take away from this graph? Okay, so if you're looking at this, right, so as temperature increase, okay, so going from lower temperature to higher temperature, you will see that most of the solid ionic compound, the solubility going to increase, right? So there are more amount that can dissolve in 100 grams of water as temperature increase, right? So all of these tell you that, right? So again, so as temperature increase, you will see that their solubility also increase as well. Okay, so that is going to be one observation that we can make from this, right? So generally, solubility increases as temperature increase. However, you will see that some of the ionic compound salt is going to have an inverse effect of this, right? So as you see, for example, here is sodium sulfate, right? So as the temperature increase, the solubility of sodium sulfate actually decrease. So why is that? In this scenario, we will need to take a look at the overall enthalpy change of the solution. Okay, so when salt dissolve in water, as we mentioned earlier, right, it's going to involve with many states, but the overall, the enthalpy change or the heat of the solution that is going to be able to dictate the effect of the temperature. Okay, so in this case, if you have the salt that produce very, very exothermic enthalpy of the solution, which means it's going to produce a lot of heat, right, as it dissolves, those are not going to be the one that want to add more heat. Okay, the reason for that is because as you add more heat, the heat that produced from dissolving this is not going to be able to expel very well. So therefore, it's going to prevent this salt to be able to dissolve more. So in this case, you will see that as temperature increase, the solubility will actually decrease. The effect of temperature can be used in recrystallization as well. Recrystallization is a purifying technique. So in this case, solid that contain impurity is going to be added to the solvent at elevated temperature to create the saturated solution. Okay, so once the temperature decrease, it's going to become supersaturated solution. And eventually the excess solid is going to precipitate out, leaving the impurity behind in the solution. Okay, so all you have to do next is just going to be filter out this solid, right? So then you are going to get only pure solid out. Okay, so that's how you purify this. Next, let's take a look at solution of liquids and liquids. Okay, so we talk about solubility of liquid in liquid before in terms of miscibility, right? So we talk about miscible versus immiscible. We treat them as black and white, right? But in reality, miscibility is actually continuous. For example, substances that are immiscible, there are still some part of it that is actually partially miscible, which means even though they are not able to completely dissolve, but there's tiny bit of it that can actually dissolve. What do I mean by that, right? So let's take a look at example of bromine in water. So we know that bromine would be non-polar molecule and water would be polar molecule. Okay, so between these, if we add them together, we are going to observe two different layers, right, between bromine and water because they both are immiscible in each other, right? So when you add them together, as what we expect, right, you see two separate layers, right? So one is bromine, right? The other is water. Okay. However, if you're looking at water now is no longer colorless, right? So this one is colorless, but this one have color. So what does it mean then? It means that some tiny amount of bromine do dissolve in water. So that means in this case, even though you add non-polar and polar molecule together, it's not that it's 100% immiscible. It's going to be only can actually be able to dissolve in the other solvent. So what does this mean then? Well, it just means that when you have polar and non-polar, they are going to still only tiny amount that can partially miscible or partially dissolve in each other. Not much, it's a small amount. Okay, so because miscibility is continuous and the continuous miscibility can be used in extraction. Now let's take a look at these four molecules. We have water, ethanol, hexane, and oil. Okay, so we are going to look at their polarity first so that way we can predict miscibility. Okay, so we have water, polar, ethanol, there are two parts of it. We have OH group that is going to be polar, and we have hydrocarbon group that is going to be non-polar. For hexane, the molecule of hexane contain only hydrocarbon, so hexane would be non-polar. And for fat and oil, right, if you're looking at this, we have the polar part and we have the majority of them would be non-polar part. What does it mean then? Well, as I mentioned earlier, right, miscibility is going to be continuous, but it's not like a dry cut. So in this case, if you think about when you add water to oil, even though they separate layer, right? So let's say if you have water here and you have oil up here, know that some tiny bit of the molecule of oil around here do dissolve in water, right? So this one right here, not much, is only partial, like tiny amount is going to be able to dissolve in water because oil fat contain this polar part. Okay, but the rest of them, which are non-polar, they are going to be away from water. So now we know polarity. The next thing is we should be able to find out miscibility, right? So we see that those that are containing polar part, they are going to be able to dissolve in each other, for example, water and ethanol. Okay, and then ethanol would be able to dissolve hexane and also fat and oil, right? Because ethanol share the hydrocarbon, and the majority of oil, right, contain hydrocarbon as well. So they are going to be able to dissolve better in ethanol and also hexane. You probably noticed this, right? So ethanol are able to dissolve in both polar and non-polar molecule. So that's why ethanol is a really good choice for the extraction of the natural product. Okay, so the reason for that is because natural product contain both polar and non-polar parts. So having different polarities, such as having ethanol, is going to allow for the extraction of the natural product for that. Okay, so and also ethanol is also safe to drink as well, right? So it's like the best choice for this. Molecule that contain both polar and non-polar parts, we refer them as amphiphilic molecules. Okay, so an example of amphiphilic molecules are soap and detergent. Okay, so as you see here, it contains hydrophobic non-polar part and it's also contain hydrophilic polar part as well. Okay, so this is the ionic end, right? It's contain negative and positive ion. And here's the detergent, right? It's contain the hydrocarbon part, which is hydrophobic, and it's also contain hydrophilic, which is the ionic end. Because soap and detergent contain both polar and non-polar parts, is going to be able to interact with both polar and non-polar molecules. Okay, so for example, the ionic end, which is the hydrophilic end, is going to interact with water. Okay, and then the hydrocarbon tail, which is hydrophobic tail, is going to be the one that interact with oil in this case. Okay, so if you're looking at how the soap or detergent work is going to be that if you have surface that contain grease, right? If you have molecule of soap or detergent, the end tail, which is hydrophobic, their hydrocarbon tail is going to interact with grease, right? And then the ionic end is going to interact with water. Okay, so eventually this action continues, right? And is eventually going to be able to separate the grease right away from the surface. Okay, so you are going to end up with the clean surface. The next thing we're going to take a look at is the solution of gas in liquid. Okay, so we're going to take a look at the effect of temperature for the solubility of gas in liquid. Here's the graph plot between temperature on the x-axis and then solubility on the y-axis. So this one tells you about how many mole of the solute that can dissolve per 1 liter of the solvent. Okay, so in this case, we are going to look at gas as a solute, and then water would be the solvent in this case. Okay, so this one right here, if you're looking at the temperature, you will see that as temperature increase, right, all of this gas is going to be able to dissolve less. So the takeaway message of this graph is going to be solubility of gases in liquid decreases with increasing temperature. So this makes sense, right? If you're looking at the carbonate beverage, right? So for example, if you pour soda pop at a higher temperature or at a warm temperature, you are going to observe that it's going to bubble out carbon dioxide more than at a cold temperature, right? Because at warm temperature, gas will not be able to dissolve in liquid well. Same thing if you put cold water in a glass, right, and leave it at room temperature, right, you are going to see that gas would be able to dissolve in liquid less, right, as it bubble out. And because gas are unable to dissolve well at high temperature, especially with oxygen, right, you will observe that as the temperature of water increase, right, you are going to end up with less oxygen. So that means at high temperature, there would be not enough oxygen available in water, right? Because oxygen are unable to dissolve in water, and that is going to have an effect on fish and other creatures that rely on oxygen in water. Okay, so let's take a look at conceptual problem here. Okay, so we have a solution that contains saturated amount of nitrogen gas and also potassium bromide. Okay, so first we need to know that this is gas, right? So potassium bromide would be the solid that dissolve in liquid. Okay, so this is at 75 degrees Celsius, is already at elevated temperature. The question asks, when the solution is cool to room temperature, so that means it's going to go from 75 degrees Celsius to about like 25 to 20 degrees Celsius. It's asking you what most likely to. So for this example, we will need to look at effect of temperature on solubility of gas in liquid, right, and of solid in liquid. Okay, so let's take a look at the first choice. Some nitrogen bubble out of solution. Okay, so this is not true because as we see before, right, solubility of gas in liquid is going to increase as temperature decrease, right? So as temperature get cooler, you can actually dissolve more of the nitrogen gas, right? So this is not true. So choice B, some potassium bromide precipitate out of solution. Is this true? Well, if you go back to the effect of temperature, you will see that as the temperature increased, the solubility of the solid in liquid would also increase as well, which means you are going to be able to dissolve more of the salt into water, right? But however, if you decrease temperature, those solid that dissolve in water is going to start to precipitate, right? And the reason why we know that it's going to precipitate because the keyword is already at saturated point. At 75 is already at saturated point. Therefore, it means that if it's cooler than that, it's going to achieve the supersaturated point that is going to allow for the excess solid to precipitate out, right? So that means in this case, choice B would be the correct answer. Last one, we are going to take a look at solution of gas in liquid. Okay, so this one, because we talk about gas, so pressure is going to have an effect on solubility. The effect of pressure on the solubility of gas can be expressed by Henry's law, which states that solubility of gas in liquid solvent increases as partial pressure of gas above solution increases. So what do I mean by that? Okay, so let's take a look at this beaker here. Okay, so this beaker here contains dissolved gas. This dissolved gas in liquid is what we refer as solution. And we also see that there are gases above solution as well. Okay, so let's say that the amount of the gas above solution and the amount of gas in the solution are at equilibrium. We call this point dynamic equilibrium, which means that the rate of gas leaving the solution is going to be equal to the rate of gas that is dissolving into solution. Okay, so if the speed of those two are equal, this is what we call is achieved dynamic equilibrium. So now I'm going to disturb this equilibrium by increasing the pressure. So I'm going to increase the pressure by reducing the volume, right? So as the volume decrease, the pressure increase, as we see in chapter 9, right, when we talk about gas. And as you see here, as the pressure increase, it's going to cause the gas above solution to be able to dissolve more into the solution, right? Until it's achieved the dynamic equilibrium again. So that is going to cause the gas particle to be able to dissolve more in the solution. Okay, so that means the take-home message of this slide is going to be, as the pressure above solution increase, you are going to see that gas would be able to dissolve more into the solution. So this scenario is the same as soda can, right? So as you see, soda can contain carbon dioxide under pressure, right? So as is at a high pressure, it's going to allow for carbon dioxide to be able to dissolve in the solution, right? So this case, you will see that the gas or the CO2 is going to be able to dissolve into the solution because the pressure is very high, right? So it's under high pressure. Okay, now if you open the soda can, you are releasing that pressure. So as the pressure above solution decreased, you are going to see that the gas solubility going to decrease as well, which means that the gas molecule will not be able to dissolve in solution anymore. Therefore, you are going to see that the carbon dioxide is going to bubble out of the solution, and that's when you are going to see the bubble is being formed. The Henry's law can also be expressed by mathematical equation as it's written here. S is going to be solubility of gas, is going to be described as the amount of gas over the volume of the solution, right? So in this case, it's going to be mole per liter. You might also see other unit that express the amount as well. For example, like milligrams or grams, right, per liter, right, or per milliliter. So any of these would work. Okay, so those are going to be the unit that describe solubility. Okay. So the next one is the P. Okay, so P is the partial pressure. We learned about this before. The unit would be in atm. And then K is going to be Henry's law constant. The unit of the Henry's law is going to depend on the unit of solubility and the partial pressure. So in this case, if your solubility is in mole per liter, Henry's law constant is going to come out to be in mole per liter per atm. Right, so another way to write this would be mole per liter times per atm, like that, right? Or another way you can write this would be mole per liter per atm. Okay, so either one of these is fine. Okay, so now let's take a look at an example of Henry's law. Okay, so Henry's law constant is going to depend on gas. Okay, so here is the list of Henry law's constant at 25 degrees Celsius. Again, the reason why we need to emphasize the temperature, because temperature has an effect on solubility of gas, right? So that's why we need to specify what temperature it is, because if it's not at 25, then all of this value would not apply. Okay, so what does it mean exactly? Okay, so another thing that I want you to cross out would be this big M right here. So this big M is molarity unit. We are going to learn this later. So right now I have not covered that yet, but just know that this big M right here is the same as mole per liter. Okay, so I will just use mole per liter from now. Okay, so if you're looking at this, what does it mean? Okay, so it means that, let's say if you have oxygen gas, right? If you have 1 atm pressure of oxygen gas, you are going to be able to dissolve 1.3 times 10 to the third mole of oxygen per 1 liter of the solution. That's what it means. Okay, so if you have 1 liter of solution, you are going to be able to dissolve this many mole of oxygen. Same thing here, right? If you're looking at helium, it means that if you have 1 atm pressure of helium, right, for 1 liter of the solution, you are able to dissolve this many mole of helium. That's what it means. Okay, so that means tell you about like how many moles can actually dissolve per 1 liter of the solution at 1 atm. Okay, so now if you're looking at this value, you will probably notice that ammonia gas actually have the highest Henry's law constant from this list. Why is that, right? So now if you think about polarity of the solute and polarity of the solvent, you will see that ammonia and water, they both are polar. Therefore, in this case, ammonia would be able to dissolve in water the best, right? Comparison to any of these, right? Because of those gas molecule, oxygen, nitrogen, carbon dioxide, and helium, those are non-polar, so they are going to be able to dissolve less in water, which makes sense, right? Because if you're looking at the exponent, they are all negative exponents, so that means they are not going to dissolve much in water, right? So, but because ammonia actually share the same polarity as water. Therefore, ammonia is going to be able to dissolve best in water. Therefore, you are going to observe a very high value of Henry's law constant. Okay, so that means the takeaway message of this is that if you see the substance that have the same polarity as water, right, so they are going to share the same type of interaction, the same type of IMF. Therefore, they are going to be able to dissolve well, and that is going to cause the Henry's law constant to be also a high value as well. All right, so now let's take a look at calculation that is going to be part of this section right here. So let's say that if you have 21% of oxygen available in the air, right, and we want to know solubility of this oxygen gas at 25 degrees Celsius at sea level, what should we do, right? So let's take a look at this. Okay, so in order to do this, we want to know solubility. Therefore, the equation we're going to use is going to be solubility. Okay, so solubility of what? Okay, so of oxygen gas. Okay, so that means it's the same thing, right? It's the S equal to KH, right, and P, right? So in this case, I specified those for oxygen. So the question is, okay, we want to find S. Do we know KH? The answer is probably, yeah, if you go back to here, right? So we know that the KH at 25 degrees Celsius, we know what that value is. So that means in this case, we know what is the value of KH. Now, what about partial pressure of oxygen? Okay, so partial pressure of oxygen, the keyword of this is at sea level. Okay, so according to chapter 9, we know that sea level is going to have the atmospheric pressure equal to 1 atm. Okay, so 1 atm is going to be the total pressure of all the gas available at sea level, right? Because that is the atmospheric pressure. So that means if you think about this, we have 21% of oxygen. What does it mean? Well, it means that 21% of oxygen is going to contribute into this 1 atm, right? So that means in this case, in order to find out the partial pressure of oxygen, we know that it's going to be 21% of the total pressure, right? Which is the atmospheric pressure. So what you're going to do is that you are going to convert that 21% into a fraction and then multiply by the atmospheric pressure, right? You are going to get 0.21 atm. So that means in 1 atm of the atmospheric pressure, it's going to contain 0.21 atm of oxygen, just oxygen. Okay, so that's what it means. So now if you want to know how much oxygen can dissolve in water at this 25 degrees Celsius, then you are going to use the Henry laws that I mentioned earlier. Note that this list is already at 25 degrees Celsius, so I can just use that, right? So I use this KH and then multiply by partial pressure of oxygen, and you are going to get 2.7 times 10 to the negative 4 mole per liter. Well, what does this mean then? Well, it means that at 25 degrees Celsius at sea level, you can dissolve 2.7 times 10 to negative 4 mole of oxygen for 1 liter of the solution. That's what it means. All right, so now let's take a look at B. Okay, so we are going to take a look at 5 degrees Celsius now. We're going to take a look at if you cool the temperature cooler, if it's like what should be the solubility of oxygen, right? So in this case, you should expect solubility of oxygen to be higher than this. The reason for that is because as you see earlier, right, as the temperature decreased, solubility of gas would increase, right? Gas will be able to dissolve more at a cooler temperature. So that's what we should be able to see here. Okay, so according to this calculation, we want to know solubility again is going to be S, right? We're going to find S of oxygen at 5 degrees Celsius at sea level. Okay, so I'm going to set up the same equation again. Okay, so now the next thing is we know partial pressure of oxygen, right? Because in this case, we already calculate that, right? According to part A, we know the partial pressure of oxygen is 0.21, right? According to 21% of the atmospheric pressure at sea level, right? The next thing we are going to take a look at is this value right here. My question is, can I use this value right here that belong to oxygen? The answer is no, right? Because this value right here is only applied for 25 degrees Celsius. Okay, so that means in this case, you will need to find the KH first, right, in order to plug this in and then solve for this, right? So in this case, we don't know this KH yet. So that means something else probably going to allow you to find out KH value. Okay, so what do we do? Okay, so in this case, let's take a look at what else is given for this problem. Okay, so this problem also given the fact that at 5 degrees Celsius, if you have pressure of oxygen 3 atm, you should be able to dissolve oxygen 183.6 milligrams in 1 liter. Oh, okay, you know solubility, you know partial pressure. Wait a second. So we can do the same thing, right? So you can add these two together and solve for that, right? Because then now in this case, KH would be the only unknown variable that we need to solve. So if I do that, I would just plug in solubility of oxygen at 5 degrees Celsius. I will plug in pressure of oxygen at 3 atm, right? Because given partial pressure at 3 atm. Okay, so in this case, if you solve for KH, your KH is going to come out to be 61.2 milligrams per liter. Remember, it stays as milligrams per liter. I'm just going to use it milligrams per liter because it describes amount per volume. So I'm not going to change. Okay, so I'm just going to leave it as milligram per liter. Now, because we know the KH value at 5 degrees Celsius, therefore, we should be able to plug in this KH value to solve for solubility of oxygen now. So now, in this case, we are going to multiply KH value that we solved from the first part and then multiply by the partial pressure at 0.21. Okay, so again, we have less partial pressure. So therefore, the solubility of oxygen here is going to come out to be less than this one that has higher partial pressure. So it's come out to be 13 milligrams per liter, which makes sense, right? Because if you think about this, right, 13 milligrams per liter mean that if you have only 0.21 atm of oxygen, right, you are going to have less solubility of oxygen than the one that have high partial pressure, right? So that makes sense that your answer come out to be less than this solubility because this one has higher partial pressure. So this would be your final answer. The reason for that is because the problem doesn't ask you specific unit, right? So you can just leave as milligrams per liter. But what I'm going to do next is I'm actually going to compare this solubility at 5 degrees Celsius, okay, to the one at 25 degrees Celsius that we just calculate, right? So that way we can have the same unit to compare. Okay, so in this case, if I convert these milligrams to mole, okay, so I'm going to divide by 1,000 milligram per 1 grams. And I'm going to convert this to mole by using molar mass. Okay, molar mass of oxygen is 16. So oxygen gas is O2. So therefore, it's going to be 32 in this case per 1 mole. Okay, so if you calculate this, you are going to get 4.1 times 10 to negative 4 mole. Okay, so I'm going to use this number to compare part A. Okay, so this is the amount of mole of oxygen, right, in 1 liter of the solution at 5 degrees Celsius. Okay, so this number should be higher than in part A. So let's take a look at that. Here, if you're looking at the solubility of oxygen at 5 degrees Celsius from part B, right, you will see that oxygen can actually dissolve more than the one that is at 25 degrees Celsius. Okay, so which makes sense, right? Because as temperature increase, the gas solubility will decrease, right? So that makes sense, right? That the one at lower temperature will be able to dissolve more. So because we talk about gas, so I'm going to tie the idea of Henry's law together with the ideal gas law. Okay, so we know from chapter 9, the ideal gas law is PV equal nRT, right? And we see that the Henry's law is the solubility equal to constant time the pressure, right? So if you're looking at these two laws, you'll probably see that pressure are in common, right? So that means in this case, I'm going to relate these two laws through the pressure. Okay, so if you're looking at this, right, so according to ideal gas law, what I can conclude with this, right, so the relationship of the ideal gas law, you will see that pressure is directly proportional to number of mole. What does it mean? Okay, so it means that as the number of mole of gas increase, you are going to end up with a higher pressure as well. Now, if you look at Henry's law, right, you will see that solubility is directly proportional to the pressure. Okay, so that means if you increase pressure, you are going to observe that solubility of gas will also increase as well. Okay, so that means if you link between these two, right, because they both have pressure in common, right, so they both has pressure in common. So that means we also can see the relationship between solubility and number of mole as well. So that means that in this case, we can conclude that solubility of gas is going to be directly proportional to the number of mole of gas as well. What do I mean by that? Okay, so it means that as you increase number of mole of gas, you are going to be able to dissolve more of gas in the solution. That's what it means. I'm going to extend this idea and apply to the case study, ocean acidification. Ocean acidification is caused by the excess amount of carbon dioxide that dissolves in ocean. Okay, so before we get into more detail of ocean acidification, I would like to show the graph that's showing the amount of carbon dioxide throughout thousands of years, okay, before today. Okay, so the x-axis represents thousands of years before today. Okay, so 0 is going to be start at 1950. Okay, and then this is going to be the current year, right? So this is going to be before that, okay, so before our time. So if you're looking at the amount of carbon dioxide, right, part per million, okay, so you are going to see that the amount of carbon dioxide is always in a cycle, but it's actually break the cycle when you're looking at the current year, right? So if you're looking at this, I want to point out that 1950 is when the Industrial Revolution happened. This is when carbon dioxide gas is going to be released from the use of fossil. And as you see, this graph right here is more significant than in the previous year before the Industrial Revolution. So if you're looking at this graph, okay, so it's going to start after the Industrial Revolution. There are two plot on this graph. Okay, so one is from the fossil fuel use, and the other one is from volcanic activity. Okay, so the annual average. You probably noticed that the amount of the carbon dioxide emitted from volcanic activity in comparison to the fossil fuel, they are significantly different, right? Just from this graph alone right here, you barely see the CO2 emit from the volcano, right, in comparison to the fossil fuel. So in this case, when you compare them, we are looking at carbon dioxide from human activity in a billion ton scale. But from the volcanic eruption is only in the million scale. Okay, so that means is like from the human activity is releasing carbon dioxide from the fossil fuel use even more, right, than the volcanic activities. Okay, so why is carbon dioxide is of the concern? Okay, so why are we talking about solubility of gas and tie back into this case study? Well, the answer is it's going to go to the ocean, right? So the ocean is considered to be the house storage of carbon dioxide gas. So it's going to absorb all the carbon dioxide gas that is being produced. Okay, so pretty much carbon dioxide gas is going to dissolve in water, right? So forming carbonic acid right here. So this is why we are learning about solubility of gas, right? Because it actually affects our real life here. So these carbon dioxide gas that dissolve in water that form carbonic acid, this carbonic acid is going to eventually dissociate into ions. So this ions is what we refer as proton. You're going to learn this more in detail in 123. Okay, so and it's going to also dissociate the hydrogen carbonate as well, okay, or what we call bicarbonate. Okay, so this hydrogen plus, the amount of this hydrogen plus or the proton here is what we call the acidity, right? So this number that is available in water is going to tell you whether that solution is going to be acidic or basic, right? So this amount, as the number of proton increase, is going to increase acidity of the solution by decreasing the pH. Okay, so it's going to be the opposite. Okay, so that means in this case, you are going to observe that acidity and pH value are going to be the opposite. Okay, so as the pH value going low, right? So for example, lower than 7, the solution is going to consider to be acidic solution. If it's above 7, it's going to be basic solution. Okay, so in this case, what I want you to know, just a general idea of that, as the number of proton increase, you should know that acidity increase, but you are going to observe the pH decrease. That's all I want you to take away from this. Okay, so that way you understand this whole lecture a little bit more. So why is this a problem? Okay, so let me take a look at this. Okay, so according to Henry's law and also the ideal gas law, right, that we see earlier, we see that the gas solubility is directly proportional to the gas mole, which means if we have a lot of CO2 emission or amount of mole of gas, as number of mole of carbon dioxide increase, is also going to increase the solubility as well, which means that the carbon dioxide gas is going to be able to dissolve more in the water. And as carbon dioxide dissolves more in water, it's going to increase, right, the amount of proton available, right? Because if you can dissolve this more, this one is going to increase, right? As the number of proton increase, we are going to observe that the pH of the ocean would decrease, right, which indicate that the ocean or the solution is going to become more acidic. Okay, so this is going to lead to ocean acidification, and we are going to observe the pH level of the ocean would decrease. Here's a graph that contains the number of years and amount of carbon dioxide and also the pH. Okay, so if you're looking at this, the red one tell us about atmospheric carbon dioxide. Okay, so it's increased over the year, right? So it's increased, keep increasing, and you would expect that the log of carbon dioxide or the amount of carbon dioxide is actually also going to go up as well. And if you compare that with the pH of water, you are going to see that it's actually going toward the decreasing of the pH. So you may ask, why is this important since the value of the pH that is decreasing is not by much at all, right? So if you're looking at this, right, so 8.13 and 8.08, so the answer is that the living organism is actually thrive only within a narrow pH. If the pH go above or beyond within that narrow, is going to disrupt their health. Ocean acidification affect corals and shellfish the most because coral and shellfish rely on calcium carbonate to make their skeleton and shell. However, the calcium carbonate would be less available in acidic water. So therefore, in this case, the shellfish will not be able to use calcium carbonate to form their skeleton or shells. And if the ocean become too acidic, it can also dissolve their shells as well that made from calcium carbonate. There are so many studies out there that talk about the effect of ocean acidification. So this is one of them. So this is talk about how it affects oyster lava. And this one is talk about how it affects Dungeness crab, right? So it's also in the news as well. So it's just everywhere, right? So this is just some real life example that we can use what we learn in class and apply to what we know in real life. Okay, so the summary of this video is that we talk about the factor that affects solubility in, for example, the first one is solid in liquid, right? So we talk about the temperature, how that affects, right? And we talk about liquid in liquid. We're looking at miscibility, right? And then we're looking at gas in liquid. We talk about the temperature effect, and also we're looking at pressure effect. And we also tied back with the ocean acidification which is the real life example. Okay, so after you finish this video, please start working on homework 11.4 as soon as possible. And if you have any question, please do not hesitate to reach out to me during office hour.